All right, so you know, let's all right, so let's take a look at a situation where we have a charge going into a uniform field. So let's say our field is out of the page here, and we'll make a bunch of dots. And let's say we have a proton here, and it's coming into this field, right? So again, if we orient our hand, we're pointing towards the right. Our field is to the back wall behind us, and the force would be downwards, right? So when this starts to come in, the force would be like this. Now, what's going to happen is it's going to start to come around like this, right? So if we continue to orient our hand, we're going to be pointing a little bit more downwards. The field is out, and at this spot right here, the force would be like this. And then if it continued, the force here would be like this. And so the force would actually make it so that it would start to go in a circle, and then it would continue in a circle if it was a uniform field. These magnetic forces are always right angles to the plane established, right? And you know, you can accelerate the particles. In this case, it'd be centripetal acceleration if it went entered a uniform field. And it could go in a helical path as well, right? If it's not perfectly lined up, you know, in that last situation we had the field like this. But let's say that, you know, it's this proton is not only going this way, but let's say it's coming out of the page a little bit like this. What could happen when it encounters the field? It could be starting to go in a loop fashion, still coming out of the screen, but, you know, going in a circle as well. Magnetic forces cannot change the speed or kinetic energy. That's because it's acting at a right angle, right? All it's going to do is it's just going to change the direction of it. And that is an acceleration, right? Because the velocity is changing, but it's not speeding up or slowing it down. That's where you need the electric fields. Electric fields can speed up or slow down particles because they act in the same direction of it, right? Parallel to the motion. But with magnetic fields, they're acting in a 90-degree angle or a portion of that. And so, you know, it's just changing the direction. You know, so they can't do work, right? They're just going to be changing the direction. So these forces are centripetal. And remember, a centripetal acceleration is v squared over r. You know, and centripetal force is therefore mv squared over r. And we can take a look at a situation here. Let's say we have, you know, a velocity going to the left and the field is coming out of the page. And so let's orient our hands. Go ahead and take your right hand and point towards the left side of the screen. Your middle finger should be coming at your face. Your thumb should be going up then. And then what will happen is eventually it'll come around to the top. And let's try that one. We're pointing towards the right. The middle finger is going to the back wall, and then the force would be downwards. So the force would be like this. And then if it's over here, you know, the velocity is towards the floor, the middle finger is towards your face, the force would be inward, and so on, right? The force is going to stay inward, and this is centripetal force. You know, and what is actually providing that force, right? Well, that's QVB sine theta, right? QVB sine theta. That's the force, the magnetic field force, providing the centripetal force, right? And then that equals mv squared over r. And we've got that, right? That's the centripetal force, and we can find that. So what's the orbital radius then of a proton that's going at 20,000 meters per second, perpendicular to a 40 Tesla magnetic field? So why don't you go ahead and try this? You can pause the clip, go ahead and draw this out, and yeah, we can try that. And this is the orientation I want you to try. Let's say the field is going into the page and the proton is going like this. So go ahead and determine the direction of the loop, and then also the, in this case, how big the radius would be. All right, so let's see how you did. The particle is going to be going in. The centripetal force is caused by the magnetic field, QVB sine theta. And we should get 5.2 times 10 to the negative 6 meters. And if we look at the field going into the page, we have our particle, proton. So we should point towards our left. Our middle finger should be coming out of, or into the page rather. So middle finger towards the screen, into the screen, our pointer fingers to the left, and so the force would be down once it's in here, the downward like that, and then it'll cause it to go in a loop that is counterclockwise. What must be the speed of an electron if it's to have the same orbital radius as a proton, as described in the previous problem? And so this is a good one to practice as well. You'll need your data booklet for this. Go ahead and pause the clip and give this a try. See if you can figure out, how fast an electron would actually need to be to have the same radius, and then you can check your progress. So go ahead and pause it, and when you're ready to check, you can hit play to continue. All right, so the centripetal force again is FB. We know the strength of that. We know we have the field, we have the charge there, and therefore, we have the mass of it, which is much, much smaller. So this would have to be going very, very quick to be able to have the same radius, and it would need to be going 3.65 times 10 to the 7th meters per second to have the same radius. And so we've got our picture here. Go ahead and try this one, and let's see how you do. If you need to go back to that screen, you can do that to get the values, and then when you're ready to check, you can jump back up here and continue. All right, so the electron's coming through, and we've got our field, and we should end up getting a radius of 1.14 times 10 to the negative 6 meters. And if the electron is coming in like this, right, we're going to be pointing to the right wall, or middle finger is going towards the floor. The force would be into the page, right? But it's an electron, so what's going to happen is it's going to be coming out of the page, and so it's going to, and I can't depict that right here. It's going to be towards your face, and then into the page, and then towards your face, into the page, towards your face, and going around like that, trying to show something three-dimensional there. The force on it would be 7.2 times 10 to the negative 14th newtons, and that's the force experience on the proton. All right, so let's say we have this electron coming in this situation. I want you to find the force on it as well as the radius on it, and what orientation that would be if this was the situation. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so the particle's coming around. The force is directed towards the middle in this case, and we should get a force of 9.6 times 10 to the 14th newtons and a radius of 8.54 times 10 to the negative 7th meters. All right, so let's go ahead and practice this one. Let's say we have a proton that's going from south to north, entering a field into the page, and I want you to figure out what the force will be. So go ahead and pause the clip and try this one, and when you're ready to check, you can hit play to continue. Okay, so we should point towards the ceiling on this one. Our middle finger is going into the screen, and the force on this one would be to the left.